Thanks for joining my session on the Java module system. I'm Serban Iordache. I'm a software engineer at Scoop Software in Germany. And my first encounter with the Java module system was a bit more than 1 year ago when we at Scoop decided to modularize one of our products. We have an open source framework called Copper, which is a workflow engine that allows you to describe your workflows in pure Java. I'm not going to talk about it today, but I encourage you to take a look at it. And by the way, the slides and codes from this presentation are available on the web, so it's not necessary to take pictures during the presentation. Just wait for the last slide where I put all the interesting links, including the link to this presentation. So we had this open source framework, which was Java 8 compatible, and my job was to make it compatible with newer Java releases and to modularize it. At the same time, we wanted that it still works with Java 8. This happened at the beginning of March 2018, a few weeks before the release of Java 10. And at that time, there were very few real-life projects that were already modularized. So it was difficult to find examples beyond simple Hello World applications that assumed an ideal world where all your dependencies were already modularized and everything worked fine. Besides, these examples showed how to build your software with command line tools, which is actually a very good thing as the first step in your learning experience. But when you move on to complex projects, you need build tools such as Maven or Gradle. And a few hours ago, Robert Scholte had a great talk about Apache Maven. Who has attended his session? Okay, so you guys know that Maven supports all Java. And Maven was pretty fast in adding support for the Java module system. Actually, back then in March 2018, when I started modularizing our framework, Maven already worked well with the Java module system. But we used Gradle to build our framework, and we wanted to stick with it. And at that time, support for the Java module system in Gradle was almost inexistent, which made my job difficult. But on the positive side, it forced me to learn more and gave me the opportunity to contribute to open source projects aimed at improving the work with the Java module system. And the good news is that nowadays there are several plugins that allow Gradle to also work great with the Java module system. So you can use both Maven and Gradle to build your modular code. Now let's talk about the Java module system. Since Java 9, the JDK is no longer a monolith. It has been split in several modules. And here you can see the module graph of the Java 9 Standard Edition platform. At the top of this picture, there are several modules related to the Enterprise Edition. So they don't really belong to the Java Standard Edition platform. And therefore, they were deprecated in Java 9, and they were removed in Java 11. Now, having code removed from the JDK means that even if you don't modularize your applications, even if you don't make any changes to your software, you may still have problems running it on Java 11 or newer versions. So let's illustrate this with a small program that prints the XML representation of an object. Sorry. So we have here a product class with ID, name, and price, and we have accessor methods for this class, getters and setters, and also a toString method. And because I want to serialize this class as XML, I put here an XML root element annotation. The main class of my application creates a new instance of this product and then marshals it and prints its XML representation on the standard output. For the sake of completeness, we also have a unit test class. There's not much to test on our product because it's only a data class, so I'm just checking if the toString method works as expected. And we build everything with Gradle. This is our Gradle build script. We only have test dependencies here on JUnit. So let's try to execute this code first with Java 8. So I'll execute Gradle run. No, I'm not in the right directory. And as you see, it printed the XML representation of our object. Now let's do the same with Java 11. And now it failed, and it says package JavaX XML bind annotation does not exist. Why? Because this package is part of the Java XML bind module, which has been removed in Java 11. So what can we do? The code removed from the JDK is still available in public repositories, such as Maven Central or JCenter. And here I compiled a table with the replacements for the removed modules. In our case, we need Java XML bind, so we need to use this library, which means that in our Gradle build script, we have to add this line. So let's do this. And now let's execute again. And now it worked. So we had problems running code on Java 11 even before starting to modularize our code. But we want to modularize it. And what should we do to modularize our code? We need to add a module descriptor. A module descriptor contains metadata, such as the module name, the module dependencies, the packages exposed by the module, and so on. And we put this information in a module info Java file, which gets compiled to a module info class, which is our module descriptor. So we put here the dependencies of our module, which can be normal dependencies or transitive dependencies. We specify which packages are exposed to other modules, which packages are opened for deep reflection to other modules, which services are used by our module, and which services are provided by our modules and the corresponding implementing class. So the Java module system provides strong encapsulation. A module can decide which parts are visible to other modules and which parts of it are hidden. But sometimes we may want to break this encapsulation. We may want to still have access to these hidden parts of a module. And we can do this because the Java compiler and the Java tools provides some command line flags. For example, we can specify that a module should export a package that was otherwise hidden. We can ask a module to read additional modules or to open a package for deep reflection to other modules. Before Java 9, we needed to put all our dependencies on the class path. Now we also have a module path, and that's where our modular code should reside. Modules are resolved from the module path, and these are the command line flag to specify your module path. Now, depending on the type of your artifact, modularized or non-modularized, and on its location on the class path or on the module path, we have 4 possible combinations. Before Java 9, we only had this combination, a non-modular artifact on the class path. Its modular counterpart is having a modular artifact on the module path. But there are 2 other combination possibles. Having a modular jar on the class path. What happens in this case? Well, all code on the class path is treated as non-modular, and it becomes part of the so-called unnamed modules, which exports all code on the class path. It reads all other modules, but it is readable only from automatic modules. Now, what are these automatic modules? They have to do with this combination, having a non-modular artifact on the module path. And when you have a non-modular artifact on the module path, it is automatically turned into an automatic module, for which a module descriptor is generated on the fly, and this module descriptor requires transitive, all other resolved modules. It exports all its packages, and it reads the unnamed module. So automatic modules are some kind of bridge between the modular and non-modular world, because automatic modules are the only modules capable of reading code from the class path. Split packages. A package with the same name is not allowed to appear in 2 different modules. But sometimes we have this situation. Sometimes we have 2 artifacts containing the same package. So in this case, the Java compiler and the Java tools allow us to patch a module, which means that we can merge all classes from a list of artifacts into a given module. For example, in this command will merge all classes in this JSR 305 jar into the Java XML WS annotation. Now let's get back to our XML printer application, and let's modularize it. Our module descriptor is very simple. We saw that we need the Java XML bind module, and we also need to open the package containing our classes to Java XML bind in order to allow the classes in this module to use reflection to create the XML representation of our object. And before trying to execute our modular code, we make another small change. I want to print the name of the module containing the XML printer class. Why? Because we saw that when we put modular code on the class path, it is treated as non-modular. It is part of this unnamed module, and in this case, getModule.getName will return null. So this is a way to check if our code is executed on the class path or on the module path. If we get here a null, the code is executed on the class path. And we will do the same with our unit test class in order to see how our unit tests are executed. Now, without making any other changes, let's try to execute this code. So I'll move to project 2, where I have the module descriptor and these changes. And now let's execute Gradle run. And it failed. It says module not found, Java XML bind. Why? Because by default, Gradle puts all artifacts in the dependency graph on the class path. So we need to tell explicitly Gradle to put these artifacts on the module path. And that's how we do it. We said that everything that was before on the class path should be put on the module path, and our class path is only an empty list of files. So let's copy this or this code into our build Gradle. Oops. Okay, and now let's try again. And now it worked, but I see here running module null, which means that the code was executed on the class path. So I also need to tell Gradle that the code should be executed on the module path. And that's how we make it. Again, we put everything that was previously on the class path and the module path, and we add our module to the list of modules to be resolved. Now putting also this in our Gradle script, let's run again the program. And now we see that it was executed on the module path because we see here the name of our module. Now let's test our code. So I'll say Gradle test. And the tests were successful, but once again, we see they were executed on the class path. So we also need to tell Gradle to execute our test on the module path. And here it's a bit more complicated because the unit test class and the class under test are in the same package. So we have a split module between our main module and our test module. And we need to patch our main module. So we merge everything from the test source set into our main module. We also need to add the JUnit module and to let our main module read this JUnit module. So let's copy this snippet in our Gradle script. But that's not all. We also have to tell Gradle how to execute the tests. And that's how we make it. Here we have additionally these add opens. We need to open the package containing our classes to JUnit. Why? Because JUnit uses reflection to process the test annotation in our code. So now copying also this. And let's execute again our tests. Now we see that the tests were executed on the module path. Another thing we may want to do is to create a distribution for our application with start scripts. And we can do this in Gradle with the install dist task. And now in the install there we will find start scripts for our program. Let's execute the start script. Again, it worked, but it executed the code on the class path. So we also need to tell Gradle how to adjust the start scripts in order to execute the code on the module path. And that's how we do it. Because Gradle generates both a bash script and a bat script for Windows, we need to adjust both of them. So let's also put this in our Gradle script. And now we will run again our install dist task. And when we start our start script, now we see that the code was executed on the module path. So let's see again what we did. We needed to tell Gradle how to compile the code, how to execute it on the module path, how to compile our tests, and how to execute them on the module path, and we also needed to tell Gradle how to adjust the start scripts. Pretty simple, isn't it? No, it's not simple, but fortunately, there is a plugin that does all those things for us. So I think you will appreciate this plugin now that you saw how much work you need to do without it. With this plugin, you only need to put it in your Gradle script and you're done. So let's go further. Let's assume you have a library which is Java 8 compatible, and you modularize this library. So you add a module descriptor, but you still want this library to be compatible with Java 8. The problem here is that you cannot compile the module descriptor in Java 8 compatibility mode. So what you need to do is first to compile all sources except the module info Java using a value less than or equal 8 for the release option. And then you compile separately the module info Java using a value greater than or greater than 9 for the release option. And when you do this, you also need to add all the files produced in step 1 to the module path. And then you just combine all the classes produced in the first 2 steps, and you have a modular jar that is also compatible with Java 8 or an earlier version. And you can do this with both Maven and Gradle. For Maven, the documentation shows you how to do this. You have here an example, POM.xml, so you only need to read this, and you will see how to do it with Maven. With Gradle, we can use again the Java Modularity module plugin, which we saw before. And with this plugin, we only need to call this mixed Java release method with an argument specifying the target Java version for our code. And that's all. Now, another thing we may want to do is to create a custom runtime image for our modular application. And we can do this with the jailing tool. A custom runtime image is a distribution that contains only the modules required by your application. So it's smaller than in the case you have all JDK modules there. And you can also create your own JRE. So a JRE with only the modules you want. But the jailing tool has a strong limitation. It can only work if all artifacts in the dependency graph are modularized. And that's scary because most of the time you have non-modularized artifacts in your dependency graph. But we can solve this problem. And to illustrate how, we will consider a small web application using Vertex that serves a page saying hello and a name, and this name is taken from the name parameter found in the URL, or if this parameter is not available, it will use a default value, this nameless stranger. The main method of our server just deploys the vertical we saw before, and the module descriptor for our application requires the Vertex core module and exports its package. We use again Gradle to build this application. We have this dependency on Vertex core, but Vertex has its own dependencies, and the dependency graph of this application has about 20 artifacts. One of them is netty_common, and netty_common uses the misc unsafe, the sun misc unsafe class, which is a proprietary API, and you should not use this class. But because netty_common uses it, we need to tell Gradle that we need this JDK unsupported module because it contains the sun misc unsafe class, and we also allow netty to read this JDK unsupported package. Let's try to execute this application. So I'll say Gradle run again. And now if I open localhost 8080, I see here hello nameless stranger, and if I also provide a parameter, it says, for example, hello jeeconf. Okay. But what we want is to create a custom runtime image for our application, and as I said, the dependency graph of this application has about 20 artifacts, and almost all of them are not modularized. Now, what can we do? There are two possibilities. First, we can use the modetect tool. And the modetect tool allows us to generate module descriptors for our non-modularized artifacts and to add it to these artifacts. So we need to do this for each non-modularized artifact in our dependency graph. And modetect provides plugins for both Maven and Gradle. Let's see how to do this with Maven. So this is our POM XML. We have here this modetect Maven plugin, and then for each non-modularized artifact, we need to configure its module descriptor. Most of the time, the only thing we need to do is to provide a name for the module, as you see here. And that's because modetect uses JDEPs to generate the module descriptors. JDEPs is a tool for analyzing dependencies, and it can also generate a module descriptor for an artifact. But sometimes JDEPs does not generate the correct module descriptor, and in such cases, we can provide the module descriptor explicitly, such as here or here. And another possibility, another option offered by modetect is to configure the directives in our module descriptor, such as requires, exports, uses, and so on, using wildcards. For example, here I specify that for this module, we want to export all packages except those containing impl in their name. With Gradle, it's similar. We need to use this modetect Gradle plugin, and we also have here the configuration for each of our non-modularized artifacts. So modetect is a clean solution. It just modularizes each dependency. If your application is complex, your dependency graph may be quite big. It's not unusual to have about 100 dependencies, 100 artifacts in your dependency graph. And if most of them are not modularized, you will have to put them all in this configuration. And if you're lazy and you think this is too much work, you can take another approach, the so-called badass approach. In this approach, you combine all non-modular artifacts in a single one, into a so-called merge module. And then you only need to modularize this merge module. And there is a Gradle plugin that lets you do exactly this. And that's how we can use it. So we specify the plugin in our Gradle script, and then we have a JLink block where we can put additional options for the JLink tool, and we can also configure the module descriptor of the merge module. Now, most of the time, this is not necessary. Most of the time, the plugin can figure out for itself what to put in the descriptor of the merge module. But in some cases, it may miss some information. For example, in the case of our web application using Vertex, it is not able to detect all the services used by our application, so we have to add them manually here. Okay, let's try to create a custom runtime image for our web application. The badass JLink plugin has a task named JLink, so I have to execute here Gradle JLink, and it will create a custom runtime image for our application. And this custom runtime image is in the build image directory. Let's see what's here. We have several directories. We have a bin directory, a lib directory, and some other directory. Let's see what we have in the lib directory first. There are several files, but we see here there is a big one, a big files named modules. And this file contains all the classes needed by our application. We can see what this file contains using the JImage tool. So I will try to see what's in this file, and we see all the classes contained here. Let's just grab for the module names. Grab. Okay, and we see that this file contains only the modules needed by our application. We have our main module, the merge module, and only the JDK modules needed by our application. So that's why this custom runtime image is smaller. Now let's see what's in the bin directory. No. There. Here there are lots of DLLs because I'm on Windows, but we also see here the Java executable, and there are also the start scripts for our application. So that's how you can create a custom runtime image of your application, even if your application has non-modular dependencies. Another thing what you might want to do is to create an installer for your application. And this is especially useful when you have an application with a graphical user interface. And you can do this with the jpackage tool, which is available in Java 13. It is based on a tool called Java Packager, which was available in JavaFX, but it was removed in OpenJDK 11. And the BEDES JLink plugin, which we just saw, provides also a jpackage task that allows us to create an installer for our application. To illustrate this, we will consider a simple JavaFX application which displays a label. This is our module descriptor. We need the JavaFX controls module, and we also need to open our package to JavaFX graphics because this application launch method uses reflection in order to create the application class. This is our Gradle script. There are two interesting things here. First, we need this JavaFX plugin, which takes care of providing the native JavaFX library for our platform. And this plugin provides a JavaFX extension where we configure which JavaFX modules are needed by our application. Then we can also provide additional options to our jpackage tool. And for this simple JavaFX application, we actually don't need to provide anything. It works without this jpackage block, but I put it here only to show you how you could use it. In this case, we provide specific options for the Windows platform. So if we are on Windows, I say that we want a per user installation and that the user should be able to choose the installation directory. But once again, we don't need this code for our small JavaFX application. We can throw it away and it will work even without it. So let's try to create an installer for this application. I'll say Gradle jpackage, and it will start creating my installer. The JLink tool is able to create custom runtime images even for different platforms than the one on which the tool runs. We only need to provide the links to the directories containing the distribution for the corresponding platform. And the BEDES JLink plugin has support for this. You can very easily create custom runtime images for all platforms on only one machine. For jpackage, this is not possible. You need to execute the jpackage tool on all platforms. So if you want to create an installer for Linux, you need to run your jpackage tool on Linux. If you want it on Mac OS, then you must run it on Mac OS, and so on. So let's see what this plugin generated for us. In the build jpackage directory, we find here this installer for Windows. And let's execute it. And now it started installing the application. It's done, and now I find here the newly installed application. I can execute it, and I say I can see the hello jeeconf message. So that's how you can also create installers for your applications. The next thing you may want to do is to create a custom runtime image for a non-modular application. And what you actually do in this case is to create a custom JRE, a runtime image of your JDK containing only the modules required by your application, and then you need to copy all the classes and dependencies of your application along with the start scripts into the directory of this custom Java runtime image. And there is also a Gradle plugin that helps you do this. This is the baddest runtime plugin. That's how you use it. The plugin provides this runtime block where you can configure options for the JLink tool, and you can also provide the list of modules required by your application. Most of the time, it's not necessary to provide this list of modules because the plugin can figure out by itself what to put here. In our case, we used here again this web application with Vertex, and in this case, the plugin is not able to detect that we need the JDK unsupported module. This was needed because of this sunmisc unsafe class used by Netcommon. So, as you see, we have the possibility to also create custom runtime images for non-modular applications. Okay, so we saw that the Java module system provides reliable configuration and strong encapsulation. You can put your code both on the class path and on the module path. You can create modular artifacts that are still compatible with Java 8 or earlier versions. You can create runtime images of your applications using the JLink tool, and you can also create your own JRE, and you can create installers for your applications using this jpackage tool. And the most important thing, use Maven or Gradle to build your code. Here you can see the link to this talk and links to the modules I have presented. So thank you. Questions?
Thank you for your presentation, and I have one global question and some question regarding the configuration. The first question is, what was the reason to move to Java 9 for your company? And okay, yeah, that's first.
So we have this this framework, which is a library. So it is used by many people, and it is possible that some of them want to use our framework, our library in a modular application. And that was the reason. We thought it's good to offer a modular library, so people have the possibility to use it in modular code. Yeah.
Did you have an experience to put it in Docker image? And how big is it?
No, I didn't try this.
Okay, no. Thanks.
I have a question. So can you tell a few words about reflection? And as far as I understood, we are moving into a way of this modularity, and soon it will be closed, like to use reflection in such way like we did it in previous versions. What is your opinion about this?
Well, when you use reflection, you need to open your packages for reflection. So depending on what's in your code and how much reflection you do, you may have to put more opens directives in your module descriptors, or not so many.
Yeah, This was my second question. And how do you know which library needs which package to do reflection? Because you showed us pretty simple examples. Of course, we know that JUnit should have access to your packages, and the packages should be open to JUnit. But what about if I have like a very complex application, and how to know which packages should I open? Or it's open, or all my packages are open to reflection by default?
No, they are not open for reflection by default. Sometimes it's difficult to know beforehand all the packages you need to open for reflection, but you get an error when you execute your application, and you see directly. So it's a bit of trial and error. There is no really a way to have from the first time something that works. Same from modules, but the plugins gives you the possibility to see what plugins do you need. For example, the JLink plugin has a task called suggest. Suggest, and this will show a list of the modules needed by your application. Okay, that's not a good example here, because here are no other modules needed by our simple Java FX application. Let's try with this with a web application. And the plugin tries to detect which modules are necessary, in our example in this, and to generate a merge module for us. So we see what the plugin tries to put in its module descriptor. So if it doesn't work, we can take this output as a starting point and then tweak this module descriptor. But as I say, for complex application, you will need a bit of trial and error.
Hi, thanks for the talk. So I've noticed that even after using a simple framework to expose a REST API, we get a huge dependency graph with a lot of artifacts. And I've noticed that most of them don't provide modularized versions of them. So what's been your experience on it? Has the whole ecosystem moved towards providing modularized versions of the libraries? Or
if you have such an application or a framework that is not modularized and it's really difficult to modularize it, you probably should not try to modularize it. As I showed you, you can still create a custom runtime image for your application, even if it is not modularized. And that's what I would do in such a case. It's sometimes totally unnecessary to fight to try to modularize an application if this is really complicated.
Yeah, can you tell a bit more about where is this line where you should consider modularizing your application?
Well, that's a difficult question, and that depends on your views. If you think modularization it's really important and it's a really important thing in order to have clean code, then you will probably try harder to modularize your application. If you think it's not so important, or if you think that you are able to provide clean code without it, you don't need to use it. We wrote clean code before, so it's possible to write clean code even without modularization. I think that's depends from person to person.
And what was the final size of your GRE for this example, for example?
Let's.
I didn't get it. It was like 25 megs or something like that.
Let's see. So this was this one. Yes, I think here was the image. But we can also do with this plugin. We can also create an archive. So I can say here JLink zip, and it will create an archive with this distribution for me. So it's maybe easier to look at this one. Is it here? Yes. So the archive distribution is 32 megabyte. Okay, thank you.